Hi, my name's Bailey Roberts, and the long term that I decided to do for my Physics 2 class was called Heat Flow in Water and Solids. My original claim was that if a heat source is only on one side of a water tub, then the one side should be consistently warmer than the other. And why was I testing this? It was to see how the heat source affects the heat flow or distribution in water. So I just wanted to see how the heat will actually flow through the water and how it is distributed through the water, like if it's all at once or how long it even takes to go through that water source. So my original procedure to test this was to use a dish, and it was a Dutch oven, and we filled it 2/3 of the way up with warm tap water, and the warm tap water's temperature was 110 degrees Fahrenheit, and we sat this dish on the range set on high, and only half of the dish was on the range, so only half of it was on the heated side and half of it we called the normal side. And we used 5-minute intervals, so every 5 minutes I would check the temperature on each side. So I would check it on the normal side and then I would check on the heated side as well. So this is the thermometer that I used. It was just a little thermometer. It was very easy to work with water because you could just sit it on the side of the pot, like I'll show here in a second. And it was just easy to track each side using this thermometer. And so this is how I had my pot. I had it sitting on that range. Only half of it was on the heated side and then half was called our normal side. And this is how I had my thermometer placed in the dish. It was just sitting on the side, and then every 5 minutes I would check it. So I would sit it on one side and then I'd move it to the other and then check that side as well. So my results for this data, it showed that the heated side temperature was consistently warmer up until that 30-minute mark, because at 30 minutes the normal side and the heated side had the same temperature. So my results explained the heated side was warmer than the other side until 30 minutes, which is when the normal side became the same temperature as the heated side. And the heated side started steaming at 10 minutes, but the normal side started steaming and forming bubbles at around 25 minutes, which is right around where it was the same temperature as the heated side. So the improved water test, I was going to use a long pipe to do this, and the water would be in this long pipe, and it would be sealed on both sides, and I would have 10 little holes for thermometers to go into, so that there were many thermometers throughout this pipe, and they would track the water's heat as we heated it from the outside. And this would have been good because there would have been more data points for it, so we could have seen how the heat flow would go through that long tube as opposed to just a smaller circle. But we never got the chance to do this because all of my supplies were stuck at the school to test this final test with the water. So didn't get to do this, unfortunately. So then I decided to test a solid. And I wanted to see how heat travels through a solid, if it's all at once or if it flows through like how it did with the water in that dish. And I wanted to see how does the solid grow as it is heated, and this is just kind of like the base question for how I would do my procedure for testing a solid. For the solid test, I used an aluminum rod, and I used a Bunsen burner to heat this aluminum rod. And I used a mirror attached to a meter stick, and as the aluminum rod was heated, it would just kind of bump into that meter stick and it would push it and then it would move it up. And there was a laser shining onto the mirror, and as the mirror moved, the laser would also move, and the laser would reflect that image onto the front of the room, and we would just track where that laser was in the front of the room. So this is the mirror that I had. It was just attached to that meter stick using tape so that it was very secure on there and it wasn't going to fall off. And this is my aluminum rod. So we had the one side clamped and the other side open because we didn't really want the other side to move as much. We wanted to focus on that one side that was going to be pushing the meter stick. And we also had that rod above the aluminum rod. We wanted to make sure that the two rods that were holding on to the aluminum rod were not moving either. So we used that rod on top as kind of a supporting system, and it would support the other two rods so that only the aluminum rod was moving when it was being heated. So for my data collection, I needed to figure out what the best way was to collect the data for this method, and I figured maybe a graph on a board would work so that I could actually track where that laser was. And I wanted to show the growth of the metal, and I thought that this might help out using that graph. So the new problem was that all of my supplies were stuck at the school, and I only had those two pictures that I had just shown, but no videos of what I had done, and I did not get to graph any of my school results. So the only solution that I had was to gather home supplies and try to mimic what I was doing at the school. So my new procedure, I would use aluminum wire instead of the aluminum rod, and I would heat this wire using an open flame wax candle. And as the wire heated, the wire would grow and then move the mirror that it was touching. And when the mirror moves, the light would also move. And I would use, my light source would be a flashlight as opposed to the laser. So this was my aluminum fence wire. It was just to mimic that aluminum rod. This is the flashlight that I used, and this was propped up so that it hit my mirror perfectly, like how my laser did at the school. And then as the mirror reflected that light, it would reflect it in that circle on the door that is being shown. And I would track this circle. This would be my 0 point. And this would be the standard because this is just when there's no heat on the wire whatsoever. This is where the mirror is shining that light onto. So this is kind of how I had it set up from my point of view, from like the wax candle, from where I had that. And you can see that the light is shining onto that mirror, and the mirror is reflecting that light onto the door. And then the wire that you can see there is going to be the thing that's pushing and moving that mirror so that it moves that circle up and down on the door. And so this is how I had my wire. I had my wire very stable so that it did not move at all. And I used tape to do this. I just taped to this solid that wasn't going to be that mobile. And I did this so that only the side that we wanted to be moving the mirror would be moving, and not that side that is taped up, because we didn't really care if that side moved. And this was supposed to mimic that clamped side of the aluminum rod and that open side of the aluminum rod. This is how I had my wire. So the wire was just kind of barely touching the mirror at this point. So this is my normal for it, my standard. And so this was so that the light wire could very easily push that mobile, the mirror, around, because I didn't want it to be too difficult for the wire to move that mirror. And then the mirror was very secure onto that surface below so that it would not move at all, so that it's only the movement of the heated wire that is occurring and there's no outside movement happening to that mirror. And then I would draw a circle. I would just kind of trace around that standard image so that this is my 0 second mark. And this is the open flame wax candle, and I would just kind of sit this so that the flame was touching the wire, and I'll show you this here because the little burnt marks on the wire are where that flame was touching. So as the wire would sit in the flame, it would push onto that mirror, and then the mirror would move, and that was kind of the whole setup. And then these were my results. I just kind of traced the circle that I was getting from each 10-second mark. So I went all the way up to 60 seconds, and I just traced what I was seeing at that point. So this is how I displayed my data. I used time, so every 10 seconds all the way up to 60 seconds I would get my displacement, and I measured this displacement in centimeters, and then I also included the uncertainty of this measurement, and I'll explain that later on, how I did the uncertainty and how I calculated that number. So this was the graph of my results for the solid test, and it just kind of shows the uncertainty, which are the little lines, and then each point is the actual displacement that we got. And we just kind of showed that at that 50 and 60 second mark it was the same, but up until that point the displacement continued to grow. So my results explained, I set a 0 for the standard point, which was that 0 second mark, and we measured the distance from that standard point to the next outer line. So we would just start at that top of the 0 standard circle, and then we went up to the next line that we saw, and then moved up to the next line, so like 10 seconds, 20 seconds, 30 seconds, and then all the way up. And so to further explain that uncertainty, we took into account the uncertainty of the measuring device and the centimeter displacement. As each 10-second mark came, we had to draw the circle rather quickly, so I just wanted to make sure that we were taking into account the uncertainty of where that line might fall. And we chose 0.1 because it is the smallest decimal value for the data, and this is only in the y-axis that we were having this uncertainty, because there isn't really any uncertainty to account for in the time, which is the x-axis. My overall conclusion, I thought it was difficult to track the heat flow in liquid because there was more uncertainty, and this maybe could have been solved if we could have done anything with that long pipe, but we didn't have enough time to do anything with the long pipe because it was stuck at the school. And as heat travels through an object, the object will quickly expand until it reaches its new standard. And the standard changes between objects, so what I mean is that the aluminum wire and the aluminum rod both had different standards. So the aluminum wire reached its standard in under a minute, which was a lot less time than it took the aluminum rod that we were using at the school to reach its standard. But I unfortunately have no results from that aluminum rod at the school, so I can't compare these standards, but that would have been an interesting thing to do, was to test like what the difference is between that standard of the aluminum wire and the aluminum rod. Thank you. Any questions?